Hello everybody! Today we will continue our discussion about signals and how we can represent them into a set of different components. And even more specifically, today we are also going to discuss how exactly are we about to find out what contribution each component has. Because if you recall, last introductory particle exercise where we try to make different shapes of different signals by adding different components and subtracting as well with different contribution, we were actually coming up with different shapes. So here you can also see that you can indeed get either this signal or this signal. Both of them consist of different kind of harmonics, but their shape is different. So that was actually what Fourier, mathematician, has proven in his theorem, that you can any arbitrary selected function represent as an infinite sum of sine and cosine components. Now, however, if we choose a finite number of these components, we can only say that it is approximately of this shape, which is still in many cases more than enough for us. Now, strange. One slide is still in Latvian, but it's fine. Its idea is that you can say that your signal Sn is a superposition, that is summation, of various so-called base functions. These base functions here are represented by this phi letter with index k. So specifically phi base function 1, in our situation it was sine wave of one frequency, phi base function 2 with different frequency, and so on and so on. And also you have this AK parameter. So if we go specifically for the example we were actually trying to implement, then we can say that's indeed our case. Specifically, we were trying to create a, let's say, rectangular shaped signal in the class. Yes, so what we had here was sine wave of sine wave of double p n versus n plus 1/3 of a sine wave 3 multiplied by 2p n versus n capital plus 1/5 of sine wave of 5 multiplied by 2p n versus n capital, and so on and so on, all the way up to some arbitrary k sine wave sorry, plus 1 versus k multiplied by sine wave of k multiplied by 2p n versus n capital. So you see, in a sense, our phi k was the sine wave of k, also depends on that, and our ak coefficient, well, was 1 versus k, as simple as that. Now the question is, how did I know that I have to use 1 versus 3, 1 versus 5, 1 versus k to get a rectangular shape? And is it possible to calculate that? Well, that's actually today's topic, and I will show you how saying that you have this as signal with amplitude 1, we actually came up with this AK being equal to 1 versus k. That was actually calculated. So until this point, I was hiding this from you. Now, all cards on table, yes, I can tell you how exactly that can be get, yes. So in our situation, like we say, we can use a sine harmonic wave or in fact cosine. And as we will see in next practical exercise, actually majority of the signals will consist of both of them. It's only some specific very, how you can say, very specific shapes are actually composed out of sine wave or a cosine wave. Well, that's actually not difficult to prove. Say, for example, I have this rectangular shaped signal centered around 0, like so. So then my main harmonic, which I can describe the signal with, would be cosine. Yes, and all the other components are going to be cosines. Now consider I have a different position of the same signal. So the signal is the same. It's only that I moved it a little bit, like so. Well, actually, no, not exactly to this point. I made it just a little bit too stretched. Let me make it comparable, like so. Well, it's still a little bit too stretched. But anyway, now, however, we see the same pattern. I maybe stretched it a little bit vertically, but otherwise the same. Now you start from 0 point, yes, and you describe it with a sine wave. And as it will turn out, this is only due to the fact that this signal was symmetric around this vertical axis, and this was anti-symmetric, yes. So if it is anti-symmetric, you can describe it as sine waves. If it is symmetric, you can describe it with cosine. But if it's none of the above, you are going to need both of them. Well, we'll get to that soon enough, and before that, we'll experiment a little bit in practical exercise. But we already discussed what are the benefits of harmonic functions. Yes, like these are, well, all around us. They describe rotation, they describe natural processes which oscillate and cycle through. They are also the components which do not really change their shape once they are passing through some systems. Now, it's also important that we can, for these harmonic functions, quite easily prove their orthogonality. Well, we care about their mutual orthogonality. We don't necessarily consider that they have to be orthogonal in general. They just need to be orthogonal between two of them. Yes. And orthogonality is observed when they are obviously different functions, not the same function, because for the same function you calculate the energy. And hence, if we take two base functions, let's say sin of double pi and sin of double pj, where I and j are not the same, yes, then if the functions are orthogonal, you would get 0 when I and j are not the same, and energy if they are the same, yes. Now, this stands true for sin versus sin versus cosine, cosine versus sin, cosine versus cosine, in any combination you'd like to, yes. So it's important to notice also that this orthogonality is going to be observed only on specific time range. So if you cut it earlier than necessary, your orthogonality will fail. And the condition is quite simple. You need to have a full number of periods for both of these functions. So like, for example, here you can see in blue color, we have one cycle, one full period of the sine wave, starting from 0, ending from 0, and two full cycles of the red line, cosine, starting from 1 and ending at 1. Yes, so now they are mutually orthogonal, and I have already discussed that in a previous lecture, how we can kind of estimate that by calculating the area underneath these lines, which is with a have a positive sign and negative sign, and how they compensate each other. Now, in this particular case, you can see that red line repeats it over, yes, so up to this point it's one cycle, up to this point it's also one cycle, while as blue line acts in reverse, yes. So basically, if you multiply this blue line with this red line, here you would get something positive, here you get the same number but negative, so in total it will be 0. Yes, so averaging out. And here are some more examples of similar stuff. Yes, now I increase the frequency and again they are orthogonal. And this combination is also mutually orthogonal. So actually, as you can see, for harmonic functions, it's quite easy to come up with this function. All you need to do is essentially just increase double p to 4p, 8p, 6p, 10p, and so on and so on. So full number of these cycles, which is 2p for each, is essentially going to give you orthogonal combination. And it doesn't even matter if it is sine and sine, or sine and cosine, yes, or cosine and cosine, that's going to happen anyway. So there are quite a few examples. Now, here you may have noticed, in addition to this blue line, I also have these blue and red stamps. These are specific samples for discrete version of this signal. Now, for discrete version, actually it's even easier than that, because you can calculate them as numbers, represent them as numbers like here, and basically just multiply these numbers one with another. So this number with this number with this with this with this. So in pairs, through all the entire list, that no matter how many we have, then you simply add them into one big number. Well, actually, that number is going to be small. As you can see here, it's going to be around 0, meaning that these are indeed orthogonal. So in our case, it's actually very easy for computer to check if they are orthogonal or not. Now again, I'm just making sure that you understand this orthogonality, because that's going to play a critical role in today's tasks to actually extract the contribution of each component from the total signal. Because without that, actually, it's not going to happen. So easily, at least, yes? Now, if we speak about analog signals, however, well, then we need to deal with a calculus and calculate this integral precisely. So basically, we already did kind of that stuff, yes? So I'm not going to stay here for long. Just that you, after open this integral, you can notice that full cycle of t, which is, say, for some period p, 2p or 4p or whatever, yes, if you put it there, yes, then you get a full period over which cosine is 0 and here also 0. So total is 0. Now, this is calculus. This is true for analog signal. For digital signals, it's much easier. Yes, you simply calculate the sequence of numbers, you multiply these two arrays one with another, and there you have it, add together to get the final answer. Now, we discussed how we can decompose, or rather than that, vice versa, reconstruct cosine components or sine components into a new shape of signal, like rectangular, triangular, sawtooth, even more funny stuff, yes? And in general, you have seen that we have some coefficient and the base function. The coefficient and the base function. So again, for the rectangular post-shaped signal, we had coefficient 1, we had this 0, we had this 1 versus 3, we had 0, 1 versus n, and so forth, yes? So that produced rectangular shaped signal. Now, if you, however, had here not 0, but 1 versus 2, you had completely different shape of the signal. So now, that matters, yes? Now, for rectangular signal, then, we can conclude that if the number k is the odd number, like 1, 3, 5, 7, it was 1 versus k. Otherwise, if number was even, it was a 0. And the spectrum, well, we kind of already even visualized it. Yes, so the component empty, the component empty, the component 0, and so forth, yes? Now the question is, given this signal itself, how do I extract out this information from it? So we tried these numbers only because I said so. I said it is 1 versus k, and you had to trust me because I said, trust me, I'm going to explain it later. So now it's later when I explain you how exactly this number came up to be. So actually, the solution is pretty simple. You need to take your signal, whichever you are analyzing, and some base function which you try to get the component contribution for. So essentially, for example, like here. Yes, here you can see some signal samples in blue line, and some component for which we try to find the contribution in red line. Now you need to calculate the scalar product between your signal and this component. Now, they do not have to be orthogonal, yes, but the fact of which components it consists of actually helps quite a lot. So if we are to say that we want to decompose some signal into some numbers and we don't know yet this number, so right now these are unknown numbers, yes, so we don't know what is a1, we don't know what is a2, we don't know what is ak, we don't know what is an. But these base functions, sin of double pn, sin of 4pn, they are easy because they do not have any unknown numbers. You know the number of samples, and your number n is just basically the number of your current signal value, yes? So the question is, how do I find out these ones? Now, this may seem to be quite a complex problem because actually there is many of them and you only have one equation. So how are we supposed to deal with that problem? Now, again, considering that this is our signal, what we are going to do, say now, I want to find out what is the contribution of A1. Or rather not A1, but let's be in more general, AK. So specifically contribution of this part. What I'm going to do to find it out is to take this entire signal, well, Sn, as it turns out, yes, and multiply it with these base functions. So I take the sin of 2pkn versus n and multiply it with my signal. Now, I calculate the scalar product, meaning that what I have to get is one number, and that one number is specifically going to be this AK. But also at the same time, we remember that our signal Sn can be represented as a series of functions, like so. Meaning, effectively, that we are going to multiply this entire series with this sine wave. So essentially, we can open brackets and multiply each with each. Now here is where this orthogonality is going to kick in, because now we know for certain that these bases are mutually orthogonal, then it's going to end up in canceling out everything except this one. So we don't have to solve this equation system. They are all going to be cancelled out because they are not this component, yes, which is sin of 2p and k versus n. So if they don't match, then their product is 0. If they do match, their product is energy A, like per definition of orthogonal components. And that's why we specifically want to decompose into set of orthogonal components. That's what we start with. We say, I am only going to use these scenes that are orthogonal, which, as we have found, is very easy to do. You take 2p, you take 4p, 6p, 8p, 10p, just with an integer number of p, actually odd number or even number of p, and you automatically get them orthogonal. You don't even have to do anything to make them orthogonal, yes? And that's actually playing a critical role because now this with this is producing 0 scalar product. This with this produces 0 scalar product. And that is very nice because it also takes along into 0 this entire contribution. These do not contribute anything for this component. So the only contributing parameter would be this AK multiplied by this energy. Because if we were not to use this orthogonal component, you would have to create not one equation, but a system of equations and solve the system of equations. Now, however, this is a linear equation with one unknown parameter, which is very easy to solve, which always have a solution. So That is as simply as that. Of course, the choice of this base function is justified with that we were planning to do this all along. Yes, so we actually wanted to use sine and cosine harmonic functions with the orthogonal base just because we knew, well, I knew that it's going to be convenient for us at this point. If we were to use some other base functions which are not necessarily orthogonal, then as I say, you would have to create a set of equations like S1 is equal to A1 multiplied blah blah blah, S2 equal to A2 blah blah blah, S3, and so forth and so forth. And then you would have to solve the system of linear equations, which is again is possible, but this puts some implications to you. You will need to have at least specific number of signal points, because if you don't, your system of equations will not be complete. You will not have enough equations to do so. So with that in mind, we can actually now say that we avoided a lot of problems by simply putting this. And as I say again, pay attention how in calculation of this energy, we also have this one versus energy. Yes, because this energy is none other than the square of your base function. 2p and k versus n capital squared, which happens to be occurring whenever you multiply your base function with this component. So it's multiplied by itself and also has k. So like this, ak multiplied by this 2p and k and squared. Or essentially, that means energy. Or not equal, sorry, but multiplied. By energy. And then we say that this entire thing should be equal to 1. Therefore, you can now express it out like 1 versus ek. Well, not necessarily, okay, not really 1, I'm not writing it correctly. So here you have this entire thing, yes, and 0 and minus 1. So your signal multiplied by the base function. So I was a little bit hasty here. Now, to express this pure contribution AK, all that we need to do is to move this in front of here. And that's the actual final formula which you can use to extract the component's value. So you have a signal, then you multiply your signal with the base function in question for which you want to find this contribution, and you get an answer, this contribution. So effectively that means whenever I have this rectangular post signal, I then generate some component, I multiply them together, find their scalar product, and get a number 1. Yes? So now, next component is 3 times faster and also smaller. Again, I take these two signals, multiply with one another, and get the number 1 versus 3. That's how I came out to know that this is 1 versus 3, because I multiplied the original signal I was intending to decompose with this component, and it produces this number. Now, this, of course, will depend on amplitude. So if this is 1, that's 1 versus 3. If this is 10, then it's going to be 10 versus 3. Obviously, that scales, yes? Now, so to conclude, only the component in question is going to produce energy, which we then normalize with. All the others automatically produce zeros and therefore can be ignored. We don't care how many of them are there. There is only one that is going to kind of react to our component and produce the energy. All the others are going to simply ignore it. So now if we simplify this expression slightly a little bit, then you will see that we actually express this component like so. Yes, and well, it kind of means that this entire thing is the energy, which it is, yes, because the components are the same. They have the same number k and k, so they produce the energy k, and here you normalize with that energy k, so you are left with just value of a. So this is quite valid approach. Yes, we start with taking our signal, remembering that your signal actually contains this component inside of it physically. There is just there already, physically, mathematically, theoretically, whichever level we are speaking about, and along with many other components. But those other components are not going to produce non-zero product with your pattern that you are searching for. So effectively that means that you only simply say that kind of no, it's summation over n, not k. Yes, so kind of just have one component, and that is it. Yes, and this component is therefore calculating by this formula that was in the previous slide. So that is actually the formula for a discrete Fourier transform. Kind of, because, well, now we can ask about questions about why we specifically used sine waves. Can't we use cosine? And it turns out that if you decide to use cosines, the numbers will be different. Transform, yes. Well, essentially, if we were trying to use cosines to find what is their contribution in the rectangular shaped signal we were using in exercise, then you would find out that all of these contributions are zeros. So there are no cosines forming this signal whatsoever. Yes. Now, in the practical exercise number 1, which we are going to make next week, I'm going to give you some individual signals as well, so that each of you have different sequence of data, and then you will see that you will have to find not only sine components but also cosine components. And only when you find both, you are going to get your signal. And if you use only one, it's not going to work. Yes. So one step ahead a little bit is that we will have to essentially use both cosines and sine waves. But the good news are that we are simply going to have a second formula that's going to look like this. Bk will be equal to 1 versus ek summation over n, starting from 0 all the way up to n minus 1, Sn multiplied by a cosine of the same stuff. So the formula is going to be exactly the same. And, well, essentially that means you'll just have to do both of them. You calculate this formula and you calculate this formula and find two components. Now, having two components actually is going to make your signal in a full and complete description. That is going to be a unique combination of signal and its components. Yes, because if we judge only by one, it's kind of not full. You can think of it, and we will actually do it like so, that they both describe a complex number. And obviously, if your complex number has, let's say, real part equal to 5, well, then there is infinite amount of possibilities how you can type infinite, well, imaginary part. So you have a lot of complex number with real number 5. But if you have condition that your real part is 5 and imaginary part is also 5, then there exists only one single complex number like that. That is this number, and it's that it. Same way it will work with A and B coefficients. So B are going to become real part, A is going to become a imaginary part. And in fact, we are even going to go as far as to say Fine, now that we have a cosines and sines, we can use something called Euler's formula and say very simple way that we will have some C components that include both of them and are represented as a complex exponential instead. Minus J, double P, and K versus N. Now, making numbers complex usually complicates things a little bit, but in this particular case, it only means that instead of having separately calculating B and separately calculating A, you will calculate C just once, and then if you want just B, you take the real part. If you want just A, you take the imaginary part. So you calculate both with one go. Now, of course, they are complex numbers and computations are going to be more intensive, yes, but other than that, no other reason not to do so. Now, let's also note one thing, that if we consider that our base functions have the amplitude of 1, yes, then we can even say specifically what is going to be exactly the energy of this base function. Well, yes, so base function of the maximum amplitude of plus minus 1. Now, it's completely up to us to choose with what amplitude we are going to multiply, but it's convenient to use amplitude of 1 because this way, actually, you don't change the scale of your signal and you don't have to consider for that later, yes? And also, by doing so, we can say that energy of the harmonic wave is going to be its effective square value, yes, because this is amplitude. Now we divide by half, we get effective value multiplied by duration. So if now your amplitude is 1, this just goes away and you get t versus 2. As simple as that. And as you can see, it does not depend on the frequency, no nothing, no phase. Just its duration is going to define what is the energy. And duration is going to be a specific number of periods either. Now in analog world, then that means your energy is going to be like this, 2 versus t. Well, not energy, but 1 versus energy, yes? So we reverse this fraction. Now, however, for discrete signals, such as in MATLAB, which we are using, instead of time duration t, we need to take its digital counterpart, its equivalent of n. That is the length of your signal. Because in a computer, it doesn't really matter anymore. There's a seconds, picoseconds, nanoseconds, years, hours, centuries, yes. It's just one unit of certain time, yes, which it happens to be stored in the computer memory. And it operates only in the sense of how many data points do you have. Whereas in real world, in analog world, it affects by what is time duration of your signal, yes. So essentially, inside a computer, things get a little bit easier because you are not tied to the specific time units. You are simply working on samples. So let's now consider some example of rectangular pulses signal formed by multiple samples. Yeah, so like here. It's not exactly looking perfectly as rectangle because I have not too much of these symbols. Now, if I repeat it 100 times, then it will look much more smooth and much more rectangular. But at this point, it doesn't really matter, and it's even better, yes, to show how this particular shape can be described. So I basically repeat +1 4 times, -1 4 times, +1 4 times, -1 4 times. And for that signal, now I am going to try to estimate these components, yes? Now, first is to display these samples. So these points are specifically shown here. +1, +1, +1, -1, -1, -1, -1, +1, +1, +1, -1, -1, -1, yes? And the red line is this base function for which we try to estimate this component. Yeah, so basically, as simple as that, we see that we now have these 2 points, we have these 2 points, we have these 2 points, and also mutually multiplying them with each other. and adding all the way into a single number. And that single number is going to be this contribution. Well, in this particular case, it is 1. Yes? Well, in fact, we can actually even try, suppose this. Why not? Yes, we do have some time. Anyway, going to finish a little bit earlier. So let's actually make this live demonstration too. Because the formulas are here, it's just that you need to simply put them in and there you have it, yes? Just to see actual number. Is it going to be, like I say, or maybe there will be some, intricacies to that. So I don't need this editor. I will just input some commands here. So my signal was 0. Then I have 4 plus 1s. Then I have 4 minus 1s. Then I have again 4 plus 1s. That's 3. And then again 4 minus 1s. Do I have a 0 at the end? No, I don't. That is my signal samples, which you can, if you want to plot. Yeah, so that's the same signal. Now I have created one function, let's call it f1, of the sine waves. Now n goes, I need to have n equal to what is the total number of my samples. So in this particular case, it's 17. Yes, let's check it. Indeed it is. So I have 4 here, that's 16 plus extra 0, that's 17, yes? And small is in range from 0 to n minus 1, so numbers of samples from 0 to 16. And now I can create a function f1, which is a sine wave of double p multiplied by n divided by n minus 1, like it says here, which again I can plot. I haven't it here. Okay, so plot x, hold on, plot f1, hold on. So yes, this is this harmonic, which I kind of, try to describe with. Yes, that is this harmonic, yes? And, well, actually, I don't think it's going to be 1. So, but let's see it. Let's see it. So what I want to do now is to say summation of, well, actually, I'm going to use matrix product instead, x, which is a row, multiplied by f1 converted to column. So now it takes row multiplied by column, adds all of that into one single number, and that is 0. Yes, essentially. So we don't have this component here at this particular shape signal. Okay. And it also looks like that it could be possible. It's not really matching well with its total shape, yes? Now my frequency is twice as high, so I go to the next component, which is now double of the speed. Yes, so now I have 4p instead of 2p. So I create a function 2 with a sine of 4p and find their product. Oh, sorry, f2. Now their product is 9.6. It's not exactly 1, it's closer to 10, I believe, approximately. Well, we'll see why that happens, but essentially, we need to remember that we also need to have this energy here, yes, which I did not compensate for. So normally I would need to actually divide by the n divided by 2, which is now closer to this 1. And indeed, it's going to be 1 because my n is actually not dividing perfectly because it's odd number. Yes. So I suppose we should have +1 maybe. Well, almost, yes, almost. But nonetheless, again, you need to consider that this is very rough. I only have 4 points, yes. I would need actually to make much more points to make it more accurate. Nonetheless, this stands, yes. So just like that, you calculate the next harmonic, 6p, f3 for 6p, and accordingly x multiplied by f3 transposed, again 0, yes. Next is f4 with 8p, now this one is accurately 0, yes, and so forth and so forth. So then if we reconstruct this signal from the components we have calculated, you would get these red points, yes, for different number of points. Now, before we finish, however, I wanted to also point out some more points. Why specifically here I was so keen on using matrix? Because, well, I could have typed like this, summation x multiplied by f1 with point, yes, obviously, like so, which would produce nonetheless the same result. Now, that is because if I deal with matrix, I can do stuff like this, x multiplied by, and I list them all here, like so, f1, f2, f3, f4, and God knows how many else I want to, yes? Then I transpose them, and you get all of them in one go. So that's actually making it much faster. You won't have to make a for loop to go through all of them individually. And you can even go as far as to say that you can create this as a cosine of this entire matrix or sine of this entire matrix. That's also possible. I'm not sure if I know how to do that properly now. I want them to be one row. So I need to specify nk. So that would be n and k. So let me try. So n is this one. K is going to be there for 1 to 4. N multiplied by k. Oh, sorry. And no, k. No, that's correct. No, k multiplied by n. So I need that to be a column like this, yes? I suppose that's what I wanted to. Now I take the cosine of that, or not cosine, but sine of that entire thing, 2 multiplied by p, multiplied by k, multiplied by n versus n minus 1. And I get all the base functions in one go. And finally, I take this product, x multiplied by transposed. And there you have them, yes? So that's actually how discrete Fourier transform is going to work. And we are going to write our own discrete Fourier transform and calculate one as of such as well, FFT of x. See, these numbers are, well, let me actually calculate the absolute numbers. Here you have this number 10.79, which is almost what we had here, yes? Though the others are not zeros. Why? Well, as I said, because this Fourier transform calculates not only sines but also cosines. And if I were to check if my signal actually has some cosines in it, that's very easy to do. I just switch sine to cosine, and there you have it. It says there is actually some cosine here with a -4 amplitude for the second harmonic. So they are both there. Now, if I plot the absolute value of FFT of x, then I'm going to see a spectrum which is in a shape which we are used to see for the rectangular shaped signal, like this. Skip, skip. Well, now it's starting to mirror because this is sampled process, yes? And as we discussed, when you do sampling, your spectrum is creating the alias here. That's when that wheel was rotating counterclockwise and clockwise. Yes, so basically that's the same. If I want to see more points, I would need to repeat this signal more often or even add more points to that. Like, well, actually, let me demonstrate that. X1 is going to be 0, minus 1, 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 minus 1. And suppose now I have 8 of them. Well, I would do smart to copy first, though. So minus 1, 2 minus 1s. And then I want to change this to plus 1s and copy that once more to have a second period. Just to show what happens. And what would happen is that I would get a higher resolution of the Fourier transform, meaning I will have more accurate results to everything that is in between. So plot x1. Now it looks a little bit more steep, yes, rather than it was before. But also I want to display now spectrums. Plot absolute value of FFT x. Hold on. Plot absolute value of FFT x1. Now x consists of 4 samples per one or 0, and x1 consists of 8 samples, so more data actually, yes? So let's see if it actually changes anything. I want just it to be a red color though. And hold off. So now you see that this is actually, well, it's a little bit different here now. Okay, let me fix that fast. I know how to fix that. So that goes for n versus n. And that goes for, so now it has 833, so that goes 32 by 33. So they now need to be scaled in the proper range because one is 17 points, another is 33 points. Yes, and obviously if I don't number them properly, they are not going to match. Now they do match, yes, and you see that they actually a little bit even moved. Now that's an effect when you have not enough resolution to find this maximum and this maximum, and instead what your system sees is how they merge together into this maximum, which kind of overlaps with both of them, yes? So in this particular case, you actually improve accuracy and get, well, more proper results, which says this is your harmonic. Here we have empty, harmonic, empty, harmonic, empty. Yes, just like it should be for rectangular shaped signal. Now, these extra points in between are produced because I have oversampled my signal, but essentially these harmonics are the ones we are interested to see. So, okay, with that in mind, now we have learned quite important stuff, which we can then next week on the practical exercise to try out and work out in demonstration. But for today, that lecture is concluded. If you have any questions, don't hesitate to ask. If not, then, well, we'll continue the next topic next week, but don't want to start it just yet. Okay, so thank you then, and see you next week.